Hi, everyone. Welcome to this webinar. We're just going to wait a few more minutes so that everyone can join, and then we'll get started. If you want, in the meantime, let us know where you're joining us from. Just make sure that when you're sending the chat, send it to everyone and not just host and panelists. That way everyone can see your messages. Right, let's get this started. Hi everyone, and welcome to this Build Chatbots That Know Your Business webinar. Today we have two speakers with us. We have Richmond, our staff developer advocate at MongoDB, and we have David, a senior manager solution architecture at Cohere. Just a few notes before we begin. So we'd like to invite you to our mongodb.local events, which might be coming to a city near you. So if you just visit the page mongodb.com/local to learn more and register, and you can enter the code WEB50 to save 50% when you register. Plus, there's a free digital swag bag that you can receive. Just a few housekeeping rules. So this webinar, I saw a lot of people asking, this webinar will be recorded and will be shared with everyone via email within the next few days. As you can tell, all participants are muted, but please, if you have any notes that you would like to share with us, you can put them in the chat. Just once more, make sure you're sending your messages to everyone and not just hosts and panelists. If you have any questions regarding anything that our speakers are going to talk about in the webinar, please put them in the Q&A box. We're going to get to your questions at the end of this webinar. And then just before we finish this webinar, we have a short survey. So please take a moment to fill this out. This will help us with any feedback that you have, and it will help us with any future webinars. With that said, I'll hand it over to you, Richmond.
Thank you, Soha. Thank you for joining us today. And very quickly, I'm just going to talk about the MAP program, which is the MongoDB AI application program, which brings the forces of the AI industry over for people and our customers developing AI applications at scale and at enterprise level. So you get the expert advice, enablement session, and get the whole ecosystem, get the whole power of the AI ecosystem to help develop your applications. On that note, I can start sharing my screen and get to some code. And quick introductions from my side. So I'm Richmond LRK. I'm a staff developer advocate here at MongoDB, and I'm focused on educating folks, developers like yourself, on how to use MongoDB within your AI application, particularly vector search. And I'll let David do a quick intro.
Thanks, Richmond. And thanks everyone for joining. I'm David. I'm at Cohere. I help lead our solution architecture team. I work with all of our customers deploying Cohere solutions into production.
And MongoDB and Cohere are here today to show you how to build chatbots that know your business. So very quickly, I'm going to give an overview of what we're going to be covering and a particular use case. So the quick overview is we're going to be developing a RAG pipeline and highlighting how MongoDB and Cohere work together to help you build a enterprise level scalable RAG pipeline. And we're going to go through the typical steps such as data loading, embedding generation, all the way to how you can handle user queries and save your chat history. The use case we're focused on today is developing a chatbot assistant that is focused on asset management. So I don't know anything about asset management, but we've created a synthetic data set that essentially could simulate the the sort of questions and answers that you might get within that sort of industry, just to give you some example of how to apply Cohere's embedding models and other models to industry use cases. On that note, we'll start off with what is MongoDB essentially. So for those of you who are not familiar, MongoDB essentially is a developer data platform where we have a bunch of product features, and included in those product features is MongoDB Atlas, and particularly vector search, which many of you know is what we use to build AI applications today, specifically the RAG applications we see today. But also, MongoDB is built on a document data model. And for developers here, software engineering background, this is synonymous with the JSON data model. But MongoDB uses an advanced version of the JSON data model, which is BSON, which allows for different storage, which allows for the storage of different data type. Essentially, this document model is powerful, universal, and very familiar to application developers. And within the ecosystem of MongoDB applications, of AI applications, MongoDB is the vector database that you can use for your RAG application. And if you're building an agentic system, you can think of MongoDB as that memory provider for your agentic system. So on that note, I'll kick it over to David.
Thanks. So for those not familiar with Cohere, Cohere is a foundation model company focused on serving the needs of large enterprise. So we think about our products in two main categories. We have our generative models and our advanced retrieval models. All these models are available as a service and available through several different deployment methods, but ultimately our generative models, which for Cohere is Command R and R+, are focused on complex generative use cases. You can think of this as normal text generation, summarization, RAG workflows, which we're talking about today, as well as tool use in other really horizon type tasks. On the retrieval side, we have our embedding model and our re-rank model. Both will be used in the pipeline today. Embeddings are really focused on representing the meaning of text. That helps you scale out applications such as classification, search, and other types of tasks. And re-rank is focused on search precision. So really driving improvements in that final output you're seeing in your search systems. And both are also available as a service, just like our generative models. Now, when we think about what we're building today in terms of a pipeline, I know we mentioned RAG, but to put a bit of a visual behind how we're actually thinking about designing this system, we have our user messages coming in on the left. We then have our steps around query rephrasing, which we'll get into towards the end and talk about how to persist those messages. We also have our query embeddings, using the embedding model to represent the meaning of that text. On the right, we'll be bringing in the data sources that Richmond described. We'll talk through a bit about text chunking and pre-processing, but it won't be the focus of this notebook in particular. We'll then show how to embed this data set and store it within MongoDB Atlas. And finally, we'll show how to do retrieval against that data, run it through our document re-ranker with re-rank, and finally generate that final answer to return back to the user. But Richmond, I'll hand it back over to you to start going through the notebook.
Yeah, thanks. On that note, we will first start with step one, which is essentially installing all our API keys. And just very quickly, we can just remove this, but those won't be working in a few hours anyway. So we're going to be installing the Cohere Python library, PyMongo, which essentially allows us to connect with a MongoDB cluster and get our collection and storage, our collection and database objects. We'll also be using the datasets library from Hugging Face to load our asset management datasets. And we also have some TQDM just for progress loading and visualizing the progress of the embedding generation. And first thing we're going to do is do a pip install of all the libraries. Then we can actually get all of this, get all our API keys into our environment. Now we move over to the data loading and the data preparation step. Just a quick overview of this data set that you're going to be working with. The data set contains some company names and ticker symbols. So these are not real companies, but each data point within a data set contains a bunch of market reports for the year 2024 and 2023. And we're just going to use this to give some background into some companies as to how they are doing in terms of price to earning, market capitalization, and dividend yields, and also some recent news. And just to simulate what happens in real life today in terms of the tech market environment. So over here in the cell, what we're first doing is using the load dataset method from the Hugging Face module, datasets module to load the dataset. So we're going to be using 100 data points, and there's just 100 data points within this dataset. So it's very small and could fit in a very limited, an environment with limited compute resource. And next thing we're going to do is actually convert our data set into Pandas data frame, which allows for efficient data manipulation using Python and visualization. And on that visualization note, we can see what our data set looks like. We can see some reports, the authors, and we can see the name of the companies as well, and the ticker symbols. Next, we then go into we create a new column which combines all the specific data attributes we want to use to generate an embedding for our RAG pipeline, essentially. So as you can see over here, I'm just selecting the company and selecting the sectors, but also selecting information on the reports for each data point. And I'm combining this into a one single one single data point within each column called combined attributes. And now what this is going to be is all this combined attributes holds all the information that we think will provide that we think captures the essence or the semantics of each data point. And this is what we'll be sending to the embedding, to the Cohere embedding model.
Yeah, so when we think about Cohere embeddings, as mentioned, the embeddings are designed to represent the meaning of the text we're passing in. So in this case, you can see the function is a simple function wrapping around the Cohere API call. And you can see that towards the middle, which is making a call to co.embed, referencing the embed English v3 model. So Cohere has several different types of embedding models. We have light versions, which embed in a smaller dimension space, which can help reduce storage costs. But by default, we use our embed English. We also have the option to use embed multilingual. Now, when Cohere thinks about building our embedding models, similar to other models, they're trained from the ground up on data for specific use cases. Particularly, we focused with our latest embedding models, V3, on excelling at noisy data. So real world data that might not always be perfect. You might have shorter snippets, incomplete passages, conflating information that might be confusing for the model itself. So we focused quite heavily on removing some of the model bias that exists in traditional embedding models. You can see this come into play with a very specific input called input type. This is a bit unique to Cohere models, but what it allows you to do is tailor the embedding you're creating for different types of tasks. And what I mean by that is embedding models can be used for multiple different use cases. You can have classification, you can have clustering, you can have semantic search. In the way in which you try to represent text changes slightly depending on those use cases. Classification, for example, you might actually want what is the capital of the United States to be quite close to what is the capital of France, because those are asking a very similar type of question. But in semantic search, I don't want those to be very close together because they're asking two very different questions. And in order to represent those embeddings most effectively, we have this input type, which slightly tailors that output embedding you're getting. So this code will help you embed not only the queries, which we'll show later on, but also the documents that we're going to store in MongoDB Atlas, which we'll go into now.
Excellent. So this is what the document actually looks like. After the embedding, we have an embedding data point, and then for each of the rows, we have an embedding for each data point. And this is what it looks like over here. So now we're going to jump into MongoDB Atlas and how to create your database and your collection. So we're going to move over to MongoDB Atlas, and I'll just show some very important information, including creating your vector search index. So once you get into MongoDB Atlas, to create a new database is very straightforward. You will see a green button here that says create, and you can just click on that button and select what cloud providers that you want your cluster to live on, and select the region as well. But one thing to note is MongoDB does allow, provides free clusters and free database for those building POCs and demos. Just click on the shed button here and follow the instructions and selecting your cloud provider, and the region, and also any additional settings. But we've already created our database, and I'll show you what that actually looks like so you can get an understanding of what we're going to be seeing in the next cell blocks. So once you have your database, you can go into your cluster, and we're going to be looking at the asset management use case database. So in the code, we're going to show you how to create this. I'm just going to increase the size of the screen here. We're going to show you how to create this in the code. And also we're going to then create a collection called market reports. So to create a database, you just click on the button, create database, and enter your database name here and the collection as specified in the instructions on the notebook. And for the market reports, you can see we have a number of data points. Approximately, we have about 100 data points with the reports and all the key attributes, but most importantly, we have the embeddings for each data point. The next part is very important because for you to be able to conduct vector search using MongoDB Atlas, you actually need to have a vector search index. And I'm going to show you how to create that. So go into the search index page, and here you'll be able to create a search index over by clicking on that button, and using the JSON editor, you can put in a JSON definition for your vector search index. Select the asset management database and also select the right collection. Give the name for this particular notebook. We're using the name vector index for index. And then you can specify the type of the index, which is a vector, the field name, which is the path to where the embedding is located on each of those documents, the dimensions of the vector embedding, which for Cohere is actually 1024. And then the similarity function we're going to be using to compute the distance between vector embeddings. So we're going to be using cosine. So just for this tutorial, you would just change this to cosine, and this would be 1024. Then over here you would have the path here will be embedding. So and then this button would turn green and you can click next. But as you can see, I've already followed the steps previously. Now we're going to go back over to the code and see what we have in a notebook. So we have all the steps for all what I've just shown written out with some useful resource links to help you create your cluster, create your database, and create your vector search index. But next, one thing we're going to be doing is actually connecting to our index. Make sure you use your environment key. And then right after that, we're going to be creating a function that can essentially connect to our vector, that can essentially connect to our cluster, our MongoDB cluster. So this function is called getMongoClient. As you can see here, we're creating a client using PyMongo, specifying the Mongo URI, and also we have the app name that we're using to create our cluster with. We're just doing some very quick validation, pinging the database to make sure it's online. The next, we actually have our Mongo client over here, and then we can retrieve the database and the collection objects. So we can start to ingest data and query data. Just for to make sure we're working with a fresh data set, we're going to delete any existing records within our data set. If you're doing this for the first time, it's going to result in a deletion of just 0, which is fine. And one thing I want to highlight is the data ingestion process. With MongoDB, MongoDB is using the document model, which essentially is a JSON-like data structure, which means that when you're working with the Python programming language, it's very easy to migrate data structures from MongoDB over to Python or vice versa without worrying about the transformations or without worrying about any complex transformation or worrying about any additional processing. So in this notebook, to actually ingest the Python dictionaries of your data set into MongoDB, it's just 2 lines. Next, I'll be talking about the MongoDB query language and vector search. And let me start with building an intuition. So with MongoDB, we can actually visualize the aggregation pipeline as an actual pipe. And within the pipeline, we have stages. And these stages are essentially operations that act on the input data and provides transformed output. If you're coming from a data engineering, machine learning, or general software engineering background, you'll be familiar with the concept of pipelines. Essentially, what you have is several operations essentially executing sequentially to provide an output. Over here, you can see a list of documents that we can have in our database, and running the aggregation pipeline with different stages, which are operations, we can get a more refined result of the aggregation pipeline itself. The key aspect of this notebook is the vector search function, and this function essentially creates the stages and places those stages into aggregation pipeline, which allows us to perform the vector search operation using the vector search dollar operator. I'm going to go through the main key parts of this function. So first we get the user query, which we then embed. And this time we're switching the input type to search query, which is more optimized for embedding user query as opposed to embedding the documents. And now we have the query embedding that we can use to conduct vector search against the embeddings within our MongoDB collection. Here we can see we're defining the vector search stage, and we call the vector search operator. And this is basically a Python dictionary, so you have that intuition of JSON-like data structure when you're working with MongoDB. So here we're calling the vector search dollar operator, specifying the index that we created over a MongoDB Atlas. You have to ensure that this is correlates to the name that you've created previously, and then passing in the query vector embedding. Next, we actually specify the path of the embedding within each of the collections, and then we specify the number of candidates we want to consider for the nearest neighbor search. And what we're going to return is the top 5 results that have the highest vector search score. And just to show how you can sequentially group, how you can sequentially arrange stages, I've also kept in another operator called a dollar onset, which removes certain attributes from the end result. So we're going to remove the embeddings from each data point that is returned, because we don't actually need the embeddings for downstream processes. Then we have the project stage. The project stage actually limits the amount of, actually specifies the attributes we want in our final results. Now, this can reduce the amount of data the data layer has to process, and this could essentially speed up the data operations that we're doing in MongoDB and reduce the data load that you're sending over to your client or to the application layer. So now we have our pipeline, which is defined as a Python list with the searches arranged in the order of operation. And then we can just call the aggregate method and pass in our pipeline and execute that to get our results.
Thanks, Richmond. So as we talk about the re-ranker, I know we talked about the topic of re-rank early on in that architecture diagram, but re-ranker you can think of as a second stage search mechanism. So you can see in this visual here, we have our queries coming in the left. We have those initial results generated by the workflow that Richmond just walked through. But then we're going to pass into re-rank, which doesn't work off the index itself, but works completely independently off of the query and document pairs, which we'll see in the code below. Now, the reason you're going to add in the re-ranker is to specifically improve search precision. So when we think about embedding-based search, I typically describe embedding-based search for those in the data science background as embeddings are the recall component. They're very good at taking millions or hundreds of millions of documents and finding a few hundred, where somewhere in that few hundred is the document you're actually looking for. Re-rank serves as the precision lift. So within those few hundred documents, it's very good at telling you if result number 5 is better than result number 10, and so on, which drives that precision improvement on search. Now, it's pretty self-explanatory why this is impactful for enterprise search. It improves the final outputs that the user will be seeing. And if you think about a search page, it improves the likelihood that the relevant piece of content is on page 1. Now, in the context of RAG workflows, where it becomes even more impactful is when you think about scaling out your RAG applications. So when we think about scaling this workflow here, which obviously is in a notebook for demonstration purposes, but moving that into production system, scale becomes quite important. And the biggest bottleneck for most applications would be the generative model. In comparison, the database, the embedding model, the re-ranking model are quite scalable. They're quite small. They're quite efficient to do even massive volumes on. The generative model is the big, slow model at the end, which really does best when it's optimized for the length of tokens it needs. So re-rank, by having a higher precision and a higher confidence that your first 5 documents, for example, are more relevant, it means you can pass less documents into your final generative model, reducing that token count you're giving to that generative model, which means you're improving the throughput, cutting down on your costs, and also improving the latency of that final system. So you're able to get more out of a single instance of a model. So if we scroll down a little bit, you'll see the code for re-rank. Re-rank is by far the simplest part to implement when it comes to this system. Not that embeddings themselves are complicated, but there's a couple moving parts there. Re-rank itself, since it doesn't work off the index, you can see the call is simply calling co.re-rank, passing in the model you'd like to use. Similar to the embedding model, we have both English and multilingual versions, and a recently announced re-rank Nimble, which is a smaller throughput-focused version of our re-rank model. In addition to the model, you're going to pass in your query along with the documents. It's important to note that while we were talking a lot about embeddings and vector stores, this is not working off of the vector. It works off of the text itself. So you're passing in the text of the query and the text of the documents. This is worth noting because it means it's a bit more flexible. You don't have to use vector-based search. You could use traditional database, based search where you're using either keywords or other methods of searching, and re-rank can still offer an improvement on top of that. You can also control how many documents you're returning from the model. So you can return all of them and simply pick the top N yourself. But the API does have the nice feature where you can return 3 of the documents if you passed in 100 as an example. And finally, we have rank fields. So often your search documents have metadata, titles, IDs, other fields that are included, not just a text blob. Re-rank lets you select which fields you would like the model to pay attention to. So if you would like to capture metadata in addition and not have to add it back in later, you can still pass that metadata to re-rank, and it simply won't be included when re-rank goes to do its semantic re-ranking. Finally, the code after this is simply to parse the response so we can get our top documents after the semantic re-ranker has gone through and reordered them. Now we talk about moving into the generative component, and you can see the example of the vector query here with the query of what companies have negative market reports or negative sentiment that might deter from investment in the long term. We can run that search and see the final scores on the right of that table in the data frame in the chart. If we can keep going down, you can see how the re-ranker gets called, and the order of those documents can get adjusted based on the re-rank model that you pass them in. Now, the final step of our pipeline, if you recall back to that architecture diagram we showed in the beginning, we've now run through vector search, setting up that system. We've now run those queries and documents through our semantic re-ranker to make sure we're getting the most relevant results, in this case, the top 3 results. Now we need to provide those back to the generative model to create our final answer. Now, in most cases, you can do some prompt engineering. The prompts themselves for RAG at a very simplistic level might be something like answer my question by using these documents, and you would simply paste in the documents. With Cohere, though, we've not only allow you to do that, we've also tuned our generative model to be very good at RAG, and we've built the API to better support this type of workflow. So you can actually see in the response field on line 12 in that cell, we make a call to co.chat. For the message or prompt, we're passing in the user's query. We're then passing in the documents, and the documents was formatted from the response from our re-rank, and this is passed directly to the model as part of the API call. We then specify Command R+ as the model. Optionally, you could also pass in Command R in this case if you wanted a bit higher latency or a bit lower latency, and then passing in temperature. What's important to note, though, is you'll notice we didn't add a custom prompt to this. We don't have an additional instruction we passed beyond the query itself. This is because when you pass in those document fields, Cohere actually takes those documents, takes your query, and inserts it into a very carefully thought out structured prompt in our backend, which we've trained the model quite extensively on to make sure you get higher performance. It also reduces the difference in answers that people are getting by their ability to prompt engineer. So we want to make this workflow as accessible as possible for folks who might not want to dive deep into prompt engineering. Now, optionally, if you would like to modify those results, you can still pass in your custom prompts. You can still pass in custom preambles to modify these outputs if you'd like. Now, when you pass that response, you'll see first we get our final answer and we get the output from the model. But additionally, because we use that structured prompt, we have structured citations that get returned. So separately from the model's raw text response, we get citation response, which you'll see in the cell below. And this returns the model's citations against the documents that were provided. So you can see it not only returns the text in which document it's referring to, but it also returns start and end indexes to use to add in, whether it be UI features, superscript citations into the answer that you're rendering in your final application. So that's what we get by using that documents parameter and by focusing a lot on building the model around RAG workflows. Now, as we move into step 9, this gets to the point where we're moving beyond what I'd call standard RAG, which is very good at single turn interactions where you're asking a question and getting a response back. In reality, you often are doing RAG or knowledge assistance in a conversational setting. So the user might be asking follow-up questions. And a common problem we see with traditional RAG without an element of query rephrasing is that the model quickly loses context. If I ask a question such as, oh, when was company X founded? And then the model answers, and I follow up with who sits on the board. Now the model has no context. If it simply queries on who sits on the board, the results would be quite poor. So what we have to do actually is monitor the conversation, keep track of the questions that have been asked before, and use a generative model to reformulate our question to capture the appropriate context. And I think I run into quite often when we talk with users of models directly, of people not quite sure where they want to persist that conversational data or store that information, because often it's put onto the user to figure out where we want to store that conversational information for each user's conversation. So Richmond, I think you can talk through here how we can actually use MongoDB to help store that context and make sure that we're keeping the queries as relevant as possible.
Definitely. Thanks for that. And so I'm just going to talk through this class that we've created here called Cohere Chat. And what this class does is it brings together all the steps we've taken previously into one class that we can just call to handle the vector search, the re-ranking, and actually sending over some chat history over to Cohere to give the model an additional context of the problem domain that we're solving for. But one thing I want to quickly show is to go back to MongoDB Atlas and show the data, MongoDB working as a data store for your conversation within the chatbot. Then we will go back to the code and see what that looks like and how to get this chat history collection functioning. So one thing you can see here is a collection called chat history. And you can notice that we're able to store the interaction between the user, and which is this question you're going to see in a second, and the response from the chatbot itself, which is the Cohere model. And we have another thing to take note is the session ID. In the code that you can be provided, you can actually start to differentiate between different iterations of interaction between the user and the chatbot. So going over to the code, here we can see we go through some basic configuration of the Cohere client, the system prompt, and then we also start to initialize our MongoDB client, again, using the strings that we have previously, or if it doesn't have the string in the argument, it will default to the localhost string. But the key thing to note here is how we're adding to the history. So for every iteration between the user and the system, which is the chatbot, we actually append the collection with or insert into the collection information of the session ID, the message that was sent from either entity, which is either the user or the chatbot itself, and we prefix with the user entity itself as well. We have a function here where we're able to then retrieve the chat history, because what we're going to do is when we're making a query for chat completion, we're actually going to start passing the chat history, a dictionary of the chat history over to Cohere to give it additional context. Here you can see we have the same re-rank functionality that David spoke about extensively earlier, using the same models, and also the rank field argument that was touched on earlier again. So very quickly, I'll show you what happens when we send a message. So when this Cohere chat calls the send message function, it expects the actual string message. This is going to be from the user. So we're going to add the initial message to the history, which is using MongoDB as a data store. So we're going to be sending a message to the chat history collection and prefixing it with the user entity. Next, with the query, with the message, we're actually going to conduct a vector search. So we're going to be using the vector search function we defined earlier to conduct vector search to get a list of documents that are closely that semantically match the query itself. Next, we'll then re-rank the documents with the same function in the same process that was explained earlier, conduct some formatting, then actually call the Cohere model, passing it some additional context, which is that chat history, passing that into the chat history argument itself. And then this is just some visualization of the response. But if you notice here, we're also storing the response to the user message back into the MongoDB database, into our chat history collection. And this is a single iteration. And this happens every time there's a back and forth between the user and the chatbot. But let's see what that looks like in action. So you call the Cohere chat and you just set up, you pass in some arguments. And generally what you have to do is just call chat and call the send message function, which I explained earlier, and just send in a query, which is what is the best investment to make and why, passing in the vector search function we defined earlier as one of the inputs to its arguments. And here we can see we have some formatted results, which includes the top 3 documents that are returned, the relevant score that comes from the re-ranking, and the final answer from the Cohere model, giving us a similar structure that David spoke about, without telling it to provide that structure itself, and also giving us a citation as well. But to see the chat history in action, you can then call the show chat history or show history method in that chat class, or the chat instance that we've created. The chat history that we've created. So here we can see, when we're viewing this, we can see the previously asked question, where's the best investment to make? And we can see the answer from the chatbot itself. And you can just send another message and then show the history again to see every single interaction being added into that collection in real time. So, and that brings us to the end of this notebook demonstration. We're going to move over to Q&A, and we can start answering any questions you have for us.
Thank you, Richmond. Let me just share my screen. So I'm just gonna launch a poll right here before we move on to the Q&A. Right, we would appreciate it if you took a few minutes just to answer these questions. So moving on to the Q&A, we have a few questions, and I'm just gonna pop this slide open for you guys. You can just scan the QR code and see where that takes you. We have a question, I think it's for you, Richmond. It was at the beginning of the presentation, and the question was, does this work only with Cohere, or can we see another LLM?
So MongoDB is agnostic to any embedded models or any models, but for enterprise use case, we've noticed that obviously Cohere is specialized for enterprise use case at scale. And David, you could speak to some of the unique aspects of Cohere.
Definitely. So I'd say on the search side, our models are, I'd argue, the best models for semantic search and semantic re-ranking. And on the generative side, I think Command strikes a very good balance between very strong performance on RAG while also being an appropriate model to serve at scale for use cases where you're doing massive amounts of queries.
Excellent. I believe that answers the question. We can move on to the next one. Let's see.
Sorry, I was on mute. So the other question was, could you explain how you debug in case the chat is hallucinating erroneous responses?
Sure. So hallucinations is really that issue that seems to be plaguing any application. And while I'd say there's no definitive way that I've personally seen to completely remove hallucinations, I think there's several steps, depending on how complex you want your RAG system to be, that you could start to explore. One, I think that Cohere is focused on already is citations. While they don't remove hallucinations completely, they make traceability far easier so that your final output, it's far easier to verify if an answer is correct. There's some more complex RAG workflows that go down this track, such as a self-corrective RAG, where you have the model actually check its own answer and potentially iterate or rerun the search. But a lot of those decisions really depend on how much latency budget and cost budget you have for each individual query. Other simpler options involve guardrails or certain protective systems to try to validate those answers with smaller models. But as mentioned, it really depends on what your appetite is for multiple generative steps compared to trying to give the user the question answer as quickly as possible.
Thank you, David. There's another question for you. Does Cohere provide guidelines to prevent hallucinations?
Guidelines to prevent hallucinations. We do have prompt guides and prompt tuners within our dashboard that you can take a look at. But ultimately, it's really about correctly using the API and making sure you're setting up the documents correctly, leveraging citations where applicable, and using appropriate prompts to help guide. So really focusing on improving the search and the documents you're passing into the generative model will have far better returns on the investment compared to trying to force the generative model to just not hallucinate. Information retrieval, I think, is the commonly overlooked part of RAG pipelines. The better your search is, the easier it is for the generative model to create that final answer.
Thank you, David. We have another question. I think it's for you, Richmond. Can semantic re-ranking take additional context or instructions as input beyond the metadata?
Sorry, could you repeat that? Just one more time?
Sure. Can semantic re-ranking take additional context or instructions as input beyond the metadata?
Okay, so as we showed with the re-ranking, we had a field called, if I can remember very clearly, it was called rank fields, and this takes the additional attributes which could include metadata to actually re-rank the actual documents, re-rank the positions of each document that you've sent over to Cohere. But this is actually David. You can speak more into this.
I could certainly add on. Yes, I'd say double on what, or plus one on what Richmond said. But additionally, it's important to note, I didn't probably explain this clear enough, re-rank is not a generative model. So when we talk about extra instructions, you're not prompting the re-rank model similar to how you'd prompt a generative model. It really focuses on assigning a relevance score between a query and a document, and in that way functions much more like an embedding or classification model. So you're not passing additional instructions into a prompt like you would with a generative approach to re-ranking.
Great, thank you both. Another question, I think this is for you, David. Please correct me if I'm wrong. Do you see an implementation path where chatbots can be plugged into automated agent settings, i.e. where the entity asking the bot is an agent instead of a human?
Yes, so I think that opens up a big can of worms around agents and agentic RAG, where you might have a RAG style system that's actually leveraged as a tool by an agent. So you can think of this in the context of customer service, for example. You might have the entry point for the user be a chat with a general purpose assistant, and that general purpose assistant might have access to tools where maybe it's updating your flight booking status or updating your address. Now, additionally, you might have access to a RAG system where maybe it's a question against a knowledge base. Perhaps that agent is actually submitting the question to the system we illustrated here, and it runs through a very similar flow. The only difference is the input actually came from another model as opposed to coming directly from a user. So yes, I'm seeing a lot of work starting to emerge around agents and agentic RAG more broadly, and Cohere is certainly focused on building out not just RAG workflows, but also tool workflows, but that's for another discussion.
Thank you. I think this is a follow-up question. How is the re-ranker different from the query in terms of embedding, whether both will be using different embeddings?
Great question. So this gets back to why do we need embed and re-rank? In a perfect world, re-rank is actually a better performing model overall. It's far better at picking up individual signals, keywords, complex relationships between a query and document. But a very key part of it is it's not nearly as scalable as what we showed with vector search and embeddings. So re-rank scales almost linearly with adding more documents. So it peaks out practically at a few hundred documents before you're starting to get into seconds or potentially even minutes of latency. That's why you typically need a first stage search, which is what you get with MongoDB Atlas and the Cohere embedding model, which is what handles your scale. That's why embeddings are designed to go from millions, hundreds of millions of results down to a few hundred, because beyond a few hundred results, re-rank would be prohibitively slow to run in a production setting. So the quality is always better with re-rank, but it simply can't scale as well as embeddings do.
Thank you, David. Question for you, Richmond, I think. Are the usage of these models included with MongoDB, or they have a different price per use? And are they available for free for non-commercial chatbot projects?
So that sounds like multiple questions in one. So are the usage of these models available for free on MongoDB? MongoDB doesn't host any of the embedding models or re-ranking models or chat generation models. What we do have is integrations with partners like Cohere to actually provide you an easy way to access these models and actually build your RAG applications with these models. So that addresses the first one. There was another second part to that question.
Yes. The second part was, are they available for free for non-commercial chatbot projects?
Okay, as I mentioned, these models are not hosted on MongoDB, but I guess maybe David, you can speak to the commercial use of Cohere's models.
Certainly. So Cohere's models are obviously available for commercial use. We target, the focus of the models is on serving the needs of enterprise. Now, in terms of consuming those models, we don't need to discuss in this channel, but if you actually look at our website, we offer various different deployment methods. You can use Cohere's managed service. We have deployments through all the various cloud providers, as well as private deployments if you're looking to run the model yourself. So we typically have deployment methods that meet companies wherever their data might be, and we're happy to talk with you more about that if it's of interest.
Thank you both. Not sure who could answer this question, but the question is, can this be embedded into a website on the front end?
So you can definitely put a chatbot on a website in the front end, and the whole RAG pipeline will be implemented on the back end. So the quick answer to that is yes, you can. In terms of how you can build that, there's different ways you can build that. That's a software engineering web development question.
Thank you, Richmond. So another question. For classification, sorry, let me just check if we've already answered that question. Well, even if we did, I'm just going to ask it again. So for classification, do you have an example that can feed the Cohere with known labeling and provide it with new document and provide answer?
Yes, it's a bit outside the workflow we described here. Now, arguably, some folks include a classification step prior to the query being sent. You can think of this back to almost chatbots before LLMs had intent routing, where you're actually trying to classify what a user is asking and potentially route it to different workflows based on that. You can use Cohere embed to do classification and then train a classifier based on that. So your embedding would actually be the feature that you're training a classifier, and the classifier in this sense could be anything as simple as a regression head or something far more complex if you're actually training a more dedicated classifier.
Thank you, David. Another question, how would this setup work if our business data has macro style data for commercial real estate and finance data like spreadsheets with numbers?
Oh, Richmond, you're on mute.
Yeah, I always make that mistake. So let me give a crack at this, and David, feel free to take a crack at this answer. But the workflow will generally stay the same when you have I guess macro style data and commercial real data with finance with numbers and spreadsheets. So with data's like spreadsheet with numbers, yeah. So your workflow would generally look the same, where you're doing the data loading, the data ingestion, and selecting some attributes within your data that or metadata that actually can capture the semantics of each data point and actually generate an embedding using those attributes you've selected. Now, building RAG pipelines and building AI application can be an experiment. It is an experimentational process, but there are loads of resources that we have on our developer center, which you'll be provided a link to, that guides you through all this scenarios that you might be thinking of within your RAG pipeline, including chunking strategies that we didn't touch on, but definitely something that we'll provide some resources on. But yeah, to answer your question, the workflow doesn't change much. A RAG pipeline is typically the same process that we've shown, with different, maybe some parts going more in depth than others.
Thank you, Richmond. I think there's another question for David. Could you talk more about the re-rank process, as in the difference between with or without re-rank?
Sure. So I think we got to some of this in the earlier answers as well, but just to reiterate, re-rank is really that quality lift towards the end, where embeddings are what I'd call, to have another analogy, a very general style retrieval. They're creating a very blurry image of your final retrieval, where it'll give you 100 documents, and somewhere in there is likely the document you're looking for. Re-rank is very good at pushing that document to the top so that your final search is far more precise and that the relevant documents are closer to the top of those retrieved results as opposed to scattered within it. That's why we call it an addition to your search. It's not a replacement for traditional or embedding-based search.
Thank you, David. We have time for 2 more questions. So I'm gonna try to read that correctly. What is the limit in top and document retrievers? For example, if a user asks, give me 100 promoters with this filter, but although I put top n equals 100, the chat only gives me maximum 15 documents.
If I understand that right, it's asking about the limitations for top end for questions such as give me the top 10 companies, or I think you said promoters. Yes, this is where designing your search system well and for your use case matters, because it raises a very good point. If you have this re-rank workflow and your top end is set to 3 and someone's asking for the top 100 of something, you're obviously going to be limited because the model is not going to be able to retrieve it. So it's important to understand how your data is stored. If you have thousands of companies and you know people might ask for lists, you potentially want to use query detection to route around the re-ranker, or potentially structure it differently and return more results to pass into the generative model. I don't think that's explicitly solved just by setting a parameter or tweaking the parameters of models. It's likely solved with the broader ML pipeline design that you take.
Thank you, David. One last question. Are there ways to handle source citation related to proprietary business data?
Not sure I understand the question. Yes, we can do source citation. How it relates to proprietary business data, I'm not quite clear on that bit of the connection. Richmond, if you understand it, please jump in. But yes, you can do citations. This can link back to data. If it's proprietary, what we commonly see, folks, is just having role-based controls for what data is getting retrieved. Therefore, when you're creating your RAG system, while we showed a very vanilla implementation of, there was no data segregation, you likely have a system where what I search for is different than what Richmond's searching for. So we might put in the same query, but it's running off of a database where we both have different accesses, and therefore I'm only getting information that I have access to. And so you can definitely protect proprietary data, and the citations are only returned for data that's given to the model. So no citation would be persisted across states. Richmond wouldn't be able to see my citations. My citations would not be influencing his answers. So you could certainly do citations against proprietary data. The proprietary part I would handle on the database side, not on the model side.
Just one last question. What is the impact of dimension number for embedding data?
Richmond can talk to the storage component. So actually, Richmond, I'll defer to you because the embeddings, the dimension size is really how many dimension outputs the model is giving. So how big that number is. In this case, we didn't talk about it too much, but it's 1024, but it's impacting what you're storing in MongoDB.
Yeah. So in MongoDB, you can store embedding with dimension size up to 4096. One thing to note is we did specify the dimension size when we're creating our vector search index, which is very important. But yeah, so it goes up to 4096 for the dimension sizes of MongoDB.
Great. I don't think we have any other questions at the moment, but thank you everyone for attending this webinar, and thank you Richmond and David for hosting it and for answering all of these questions. Just a reminder, everyone's going to receive an email with the resources that we talked about and with the recording of this session. And yeah, hopefully we will see you in some other future MongoDB webinar.
Thank you all for joining.
Bye, guys.
Thanks, everyone.